Hello. Hello, good evening. Hello, guys. There's quite a few of us tonight. Welcome. Let's have a few more minutes to let the other people be able to join in. Maybe another minute or two. All right. Good evening, engineers. Welcome. Welcome to another edition of Even Learning. My name is Donny Gabriel, and I am your host for tonight. For this evening, we will be discussing about the overview of mechanical ventilation calculation. Before I continue, can you guys see my screen clearly? Can you guys hear me clearly? Okay lang ba? Any thumbs up over there so I know that you guys are okay? All right.
Yes, sir. Yes, sir.
Okay. So can hear, can see. So again, oops. We're going to discuss the overview of mechanical ventilation calculation. It is part of the ACMV series. We are actually on part 2. The first part is the heat load calculation. Second part is the mechanical ventilation calculation. Third part will be happening next month. Will be the overview of duct design and so on. We have two more, the piping design and the ACMV. So now we are at the second part, mechanical ventilation calculation. Again, I am Donny Gabriel. I'm a professional mechanical engineer specializing in ACMV. I graduated a Bachelor of Science in Mechanical Engineering in the Philippines. I also recently received my MBA from Amay University and started working here in Singapore. So I'm based in Singapore way back in 2009. So anytime that you have any questions regarding this training or regarding this session, you can just interrupt me, say your question, and we'll deal with it right there and then. If at any time after the training or after you have watched this training session, you have some questions for me or you have some comments or suggestions, you can reach me through my email at evenlearning.sg@gmail.com, or you can message me. My phone number or my mobile number is listed below. Okay. So again, we're going to discuss the overview of mechanical ventilation calculation. Right. We're going to talk about 3 items. So 3 major topics. First is ventilation spaces. Second is the ventilation requirements. And third, all about air pressurization. Oops. All right. So first, ventilation. What is ventilation? Ventilation is the intentional introduction of outdoor air into a space. So when there is a space and air is passing through it without any help, that is without any change in its properties. For example, you didn't cool it, you didn't do anything about it. It's called ventilation. Okay. So there are 3 types of ventilation. There are natural ventilation, mechanical ventilation, and mixed mode ventilation. So natural ventilation is you don't know anything, you don't do anything. So you just open up a window or just make an opening, air naturally passes through. That's called natural ventilation. But when you use mechanical equipment such as fans and blowers to introduce air into a space, that is called mechanical ventilation. But sometimes there are areas to which they are mixed. So part of it is natural ventilation, another part of it is using mechanical fans. That is called mixed mode ventilation. So here's one example of the mixed mode ventilation. This is a train station. So on top it's open, so the whole platform is actually open. So there's natural ventilation coming in. But inside the station, they also have fans. So fans are still pushing the air from one point to another. That's called mixed mode ventilation. What is ventilation used for? Ventilation is mainly used for 3 types, 3 purposes. First is to control the indoor air quality or IAQ. This is to have better quality inside the space and better air quality. Second, to control the temperature through air motion. So you're introducing air, so it won't be hot or it won't be too cold. And third, as to satisfy other aspects of the space. For example, there are air dilution or exhaust requirements or any other objectives. So yung first 2 objectives, the first 2 objectives is first to have a breathable space to improve the indoor air quality suitable for breathing. Second is to control the temperature. And third, any other aspects or any other requirements that needs to be satisfied within the air, within the space, sorry. So that's the 3 purposes of ventilation. Questions so far? None? No question? Let's continue. Let's talk about first the indoor air quality. How are we going to use ventilation to improve the indoor air quality of a space? Right. Example is a wooden shed or a wood shop. So naturally, because it's a wood shop space, people will go inside and do some work, do their work inside, do some woodworking. So let's say that the floor area of this wood shop is 30 square meter with a room height of 3 meters. So this is our example. 30 square meter space with 3 meter height. The ventilation required for this wood shop can be determined by using this formula. M is equal to AR, where M is the airflow rate, the total amount of air that needs to be pumped in or needs to be passing through this wood shop. A is the floor area and R is the outdoor rate. So where are we going to know? Where are we going to get this outdoor rate? Another way of getting this ventilation requirement is by having occupancy times R, or M is equal to the number of people inside times the room area. Why are we interested in the occupancy, because the purpose of our ventilation is to have indoor air quality, or to have this space suitable for people, suitable for habitation, suitable for breathing requirements. So that's a two ways that we can give me a minute, please. Sorry. Apologies on that. So by having this people going inside this wood shop, we would need to know what is the acceptable amount of air needs to be pumped into the space, so that people can easily or have adequate quality of air. So these are the two formulas. First is, this formula is based on the surface area. Second, this formula is based on the number of people inside. So this table is from ASHRAE Standard 62.1, 2009. This table 6.1, tells us the minimum ventilation rates. So this is where we get our values. So for this formula, this outdoor air rate, these are, can be determined using this table. So it says here on a wood shop or a metal shop, we would need around 5 liters per second per person, or 0.9 liter per second per meter squared. Occupancy, this occupancy is also determined by this table 6.1. You have it here at 120 people per 100 meter squared space. So let's see. Our example earlier was a wood shop. So this wood shop was a 30 square meter times 0.9. This 0.9 came from here. 0.9 liters per second per meter squared. So we will get 27 liters per second. For our occupancy, we had 20 people per 100 square meter space. So that's 20 people times 100 per 100 meter space, multiplied by our floor area, 30. So we will have an estimate of how many people are inside this area, times 5 liters per second per person. 5 liters per second per person. So you will see, you will get two different numbers. So these numbers would seldom be equal, no? So these numbers will always be different. You will get the higher number. Whichever is higher on these two equations, you will get this one. You will get the higher value. Higher value meaning, if you get the higher value, of course, the other requirement can easily be satisfied because you're already using the higher value. So that's for our indoor air quality. There's another equation. This equation is the number of flow rate is equal to the volume of the space. Previously, we were just considering the floor area of the space. Area only, so area only, regardless of how high or how big this wood shop. We are only considering its horizontal plane. What if we consider the vertical plane? So based on this equation, the amount of air needs to go here will be based on the volume of the space times the required air change, meaning how many quantity based on its volumetric quantity needs to be changed in an hour. That's why air change per hour. So again, our example is a floor area 30 square meter, room height is at 3 square meter. Using this table, this is SS553 Code of Practice for Air Conditioning and Mechanical Ventilation in Buildings. This one is Singapore code. This is the local code. It says here on the workshops, I would need about 6 air change. So let's plug it into our equation. So 30 square meter times 3, this is the volume, times 6. It will give me 150 liters per second. You would see, no? This 150 liters per second is way, way, way higher than our previous calculation for 27 and 30. So which one are we going to use? Are we going to use this 30 liters per second, or are we going to use this 150 liters per second? What do you think? 30 or 150? Take note.
150.
Take note that this one, this is a local code. This one, this is an international code. So this code is taken from ASHRAE standard international code. This one is taken from SS553 local code. So what do you think? Which one should we use? The local code that says 150 or the international code that says just 30? 30 is enough. 30 will do. What do you guys think? Any thoughts? Any thoughts on that?
Depends sa standard, sir.
Depending on the standard. All right. We will get back to you. We will get back on that statement. Thank you very much for participating. Huh? Right. In any other areas or any other rooms, the international code, actually standard 62.1 of 2009, gives you on other areas. It also gives you exhaust requirements. So for example, here, no, this one is supply and exhaust. However, there are areas that only requires exhaust, so which means negative value. Exhaust rates. We will get back to this later. But the exhaust requirements for space is given by this table. Kanina, earlier our table was table 6.1. This one is 6.1, minimum ventilation rates. But there are areas that only requires exhaust. So table 6.2, the next table, is the minimum exhaust rate. So this table 6.2 is also taken from ASHRAE standard 62.1. Ventilation rates is mainly used for, ventilation is mainly used for taking care of IAQ. Earlier, we have two codes. One is ASHRAE standard 62.1, and the other is the local standard SS553. In the Philippines, I think it's a PSME code, if I'm not mistaken, PSME code of 2020 ba or 2019. So here in Singapore, the local code is SS553, international code, ASHRAE standard 62.1. Just to make sure, the local code supersedes the international code. Whenever possible, always use the local codes. If local codes doesn't allow, or local codes doesn't refer to, or local codes doesn't say anything specific, then you can use your international codes. So in my case, the international code says only 30 LPS will do, but the local code says 150 LPS is needed. I must follow the local code of 150 LPS. Why? Why does the local code supersedes the international code? Because the engineer who's going to sign this is presumably local. So which means he knows what's better for their locality. The international codes is just as that, international, generalized. But local codes, sometimes you don't know, there are different areas or different applications for each area that's unique to their locality. That's why local codes is always higher than the international codes. Only when the local codes is incomplete, or only when the local codes does not specify, then you refer to international codes. Okay? Question? Question so far? None? No question? Okay. Let's go on to the second purpose of the ventilation. Second purpose of ventilation is to control the indoor temperature or control the temperature within the space. Right? This is to control the air movement for the benefit of comfort. So this is the key word here, huh? Thermal comfort, so that people will be at least a bit comfortable. What is the comfortable temperature for people? Roughly around 35, something like that. Okay, let's have an example here. An example here is a lift motor room. This is a motor room, so which means there's only motors here. These motors are serving the lift. So sometimes when one of the lift breaks down, needs servicing, people will enter here. The technicians will enter here and work on some of the motors. So because people are working here, some of people are working here, and the motors are generating heat, we have to expel that heat. But we don't need to expel a lot because usually people are not here naman. So let's say that the motors here are generating 500 watts. Let's assume that the floor area here is also 30 square meter and the room height is about 3 meters. Okay, so let's see. First, let's determine the amount of air needs to be ventilated for this room. We will use this formula. Q is equal to mCp delta T, where Q is the amount of heat or heat gain, M is the amount of airflow, Cp is the air specific heat, and T is the delta T, the difference in temperature. Okay, what is the difference of temperature are we talking about? Okay, the what do you call this? The amount, sorry, not amount. The motor, there you go. The motor rating, the motor is rated at 40 degrees Celsius. Where did we get that 40 degrees Celsius? This 40 degrees Celsius is usually the temperature of air needed for the motor to work. The motor is the one generating heat, and he needs at least an air passing through to cool down the motor for the temperature should be at least 40 degrees Celsius. So this room must be at least 40 degrees Celsius so that the motors inside for the lift motor rooms would work. 32, where did we get the 32? 32 is the design outdoor air temperature. Since we are assuming that the air that will be used to ventilate the space will be from the outside. So this is the outside temperature. This is the minimum temperature needed for this room, or sorry, maximum temperature needed for this room to be in so that these motors will be operational. So that's how we get the 40 and the 32. This 500 watts was given before. So plugging in our values, 500 watts divided by 1 times the difference of 40 and 32 will give us about 187.5 cubic meter per hour. So this room needs about 187 cubic meter per hour of air at this temperature so that it will be maintained around 40 degrees Celsius. If you pump in more, then of course this 40 will drop down a little bit. Question? Wala pa naman? No question? All right, let's continue. Okay, again, this 32 comes from the local code, outdoor air condition. This 40 is the acceptable conditions for the motor. Please refer to your manufacturer. So sometimes the manufacturer would say 45, sometimes 44, sometimes 50. So depending on the manufacturer, no? Maximum of people working inside the room is about 35 to 40. So 40 is still within the range, a little bit uncomfortable, but still workable for some people. So 40. Another example. Oh, sorry. Going back. 500. 500 is estimated number. We did not calculate the room heat load for the actual room heat load. We just threw in a number to assume. So this 500 is an assumed value. Okay. So let's use those same numbers. So we are only using these numbers so that it will be easier for us to calculate. But the principle is the same. Okay. So again, for example, this is a laboratory. The total heat load for the laboratory is 500 watts. So we did not do an actual heat load calculation, but we assume that this room is generating 500 watts. Okay. Floor area of the laboratory, again, 30 square meters. So you would notice, no? You would notice our total heat load is always 500 watts. So it's an assumed value. Our floor area is also around 30 square meter. Is also an assumed value. So let's say our room height is about 2.5 meters per second. Also an assumed value. Our design temperature for this laboratory is about 24 degrees Celsius with a humidity of 50%. SHR, sensible heat ratio. What does SHR mean? SHR means there's no latent heat inside. All sensible heat. That's why SHR, sensible heat ratio. All this 500 watts is sensible heat. Okay, so this is the assumption. These are the given for our laboratory. 500 watts, 30 square meter, 24 degrees Celsius. Right? So again, using our formula, 500, Q is equal to mCp delta T, where Q is the total heat load, M is the air flow rate, Cp is the specific heat of air, delta T is the difference of temperature. Okay, so 500 watts, even from here, 500 watts. 1 kilojoule per kilogram per Kelvin is a constant, a specific heat of air. 24, our design temperature, 24. 13, so where did we get this 13? We will discuss where we get this 13. So plugging in these numbers, multiplying these ones, and subtracting these ones and dividing this one, you will be able to get 136.4. So this laboratory, so that we can maintain it at 24 degrees Celsius, needs to have 136.4 cubic meter per hour of air. Where did we get this? 13 is the dew point of 24 and 50. So if you have this 24 and 50 and you would use your psychometric calculator, the dew point or the saturation temperature of this condition is 13 degrees Celsius. So based on the saturation or the dew point temperature and the room condition, we are able to determine the amount of air needed for this laboratory. This 24 is as per code of practice or local code SS553, design indoor air temperature. So other codes, for example, when I was practicing in the Philippines, the design temperature is at 23 degrees Celsius. Now it's at 24 degrees Celsius here in Singapore. So depending on your local code, what is the design indoor parameters? So this 24 and 50 is the design indoor parameters according to this code. Question? No question? Okay, let's continue for a little bit. All right. Third and last. Sorry, not third. Part of the second one. Ventilation is also for air motion, to move air accordingly. Okay? Why do we want to move air? We want to move air so that we can control the pollutants, we can control the odor, and we could control the temperature. Pollutants may be something that's hazardous, for example, acids, solvents, odor, the foul smell, and temperature, so that the cold air doesn't, or the hot air doesn't go to the cold spaces. So that's why we use ventilation. Example. One example here is this is a restaurant. Restaurant, you have your dining area here, you have your bar, you have your toilet, and you have your kitchen. Okay, let's go one by one. We want to control the pollutants. Where are the pollutants here in the restaurant? The pollutants, of course, are from the outside. The dust from outside, we don't want them to go inside. Those are some of the pollutants. Odor, the foul smell from the toilet, of course, you don't want it to go into the dining area. And temperature, of course, the hot air from the kitchen, you also don't want it to go to the dining area. So that the people in the dining area will have a wonderful experience. They don't have dust from the outside, they don't smell the foul smell from the toilets, and they don't feel hot from the burning kitchen, right? Not burning kitchen, from the burners inside the kitchen. Okay. All right. So how do we do that? What we do is we map out the direction to which the air will pass through. So example, kitchen, we exhaust out 100 cubic meter per hour. Again, these are assumed values. These are not calculated values. These are assumed values. Assuming that the kitchen requires 100 cubic meter per hour, so you put in a fresh air of 90. So you're exhausting out 100, but you're only putting in 90 from your fresh air. So what will happen? Because of the difference, 100 to 90, some of the air will be passing through from the dining. This 100 cubic meter per hour will create a negative pressure. Because of this negative pressure, it will suck in from the kitchen, and other air from the dining area will be pushed into the kitchen. So instead of air going out of the kitchen, you are now ensured, that the air is going to the kitchen because of this difference. So by providing difference from your difference from your exhaust to your fresh air, you are creating negative pressure. So air from the adjacent area will be going in. So opposite principle here in the dining area. In the dining area, you don't have exhaust, but you're pumping in 70 cubic meter per hour. Where will this 70 cubic meter hour go? Because you are pumping in 70 cubic meter hour, this area will become positively pressurized. Because it's positively pressurized, air will naturally want to go out where it is easy. So because they are opening here in the kitchen, of course, some of the air will go out to the kitchen. Some of the air will also go out from the doors. Okay, so now you are ensured that none of the pollutants will go to the dining area because you are pumping in air and it's pushing the air out, preventing the pollutants to come in. But you can also see you're pumping in 70, going out is 10, 10, and 10. That's only 30. Where will the other 40 will go? The other 40 will go here to the toilet. This 40 square meter is aided by the exhaust fan rated at 20 cubic meter per hour installed inside the toilet. So the toilet will be sucking in 20 cubic meter per hour, and then another 20 cubic meter hour for the other side of the toilet. So you're assured that 40 cubic meter per hour will be passing through from the dining going to the toilets, preventing the foul smell from the toilets going to the dining area. Question so far? All right. Wala namang question? No question? So using positively pressurized and negatively pressurized spaces, using the difference in exhaust air and fresh air, we create the positive and negative, positively and negatively pressurized spaces. We are able to control and predict where will the air go, or what will be the motion of air inside the space. Okay. Just take note, when you exhaust out, the fresh air has a minimum, what do you call this? Minimum distance to prevent cross-contamination. For, how do I say this? Same plane, linear, minimum of 5 meters. So your exhaust should be 5 meters away to your fresh air, so that you would ensure that whatever you exhaust here doesn't go back to the other side. All right. Another one is there are areas that are called class areas, which means this table will help you determine which air can go from which area. So for example, areas from here, can it go here or can it go here? Or areas from the dining, can it go to the kitchen? This table 6.1 minimum breathing zone, same table as we used earlier from the ASHRAE standard 62.1, will tell you which class. So which means class 1 can, air from class 1 can go to class 2, but air from class 2 cannot go to class 1. So on and so forth until, if I'm not mistaken, this is up until class 4. So air from class 3 cannot go to class 2 and class 1, but air from class 1 can go to class 3. Air from class 2 can go to class 3. So in our example, we're using a restaurant. So based on this occupancy from the bars and cocktail lounges, there you go. These areas cannot go to these rooms. So conference room, corridors, break rooms, so they cannot go. But the air from these areas can go here. Of course, air from here can mingle with one another. So air from the cocktail can go to the dining area. Air from the kitchen can go to the cocktail. Yes, they can be interchanged. But from one class to a higher class, cannot. Higher class to a lower class, can. Okay, so check on your standards. We are using ASHRAE standard 62.1 version 2019 for ventilation of acceptable indoor air quality. Question? No question? All right. So here we also discussed the cross-contamination. This is the table 5.1, again from the same standard, will tell you what is the minimum distance. So we said earlier 5, so this is the one, class 3 exhaust and relief 5 meters. So this one is from here to here is 5 meters. You can also see some of the other areas where it requires more. For example, if you have a thoroughfare or high traffic volume, 7.5. Truck loading or bus loading, 7.5. So usually it's about 5, 10, 7.5. So for here, cross contamination for kitchen to the fresh air is about 5 meters. For other applications, for other purposes, you can use this table 5.1, to determine how far your exhaust and your fresh air is needed. What is the distance needed? Yeah, for example, here, this one is a car park. Car park, you can see the exhaust point. The exhaust point is a little bit low, on the low side. Why? Why the exhaust point on the low side? Because the exhaust from the cars are also low level, so that it won't go up and it won't accumulate on top. It's exhaust out on a low level also. So this is one example of it. Another example for car parks is the exhaust of the car parks, at least 50% of the exhaust air shall be extracted from the low level. This is based on the local code. So this installation of a car park at a low level is actually preceded by the local code. Okay. Again, the local code supersedes the international code. The local code is more important. We need to follow the local code first before we even consider the international. We only consider the international code if the local code is incomplete or the local code does not state. So that's how we control the indoor temperature and air motion for using ventilation. Last but not least is to satisfy other requirements. The one reason that we use ventilation is to satisfy other requirements or other objectives as required by, example, equipments. So another one good example is requirement for fire safety. So we use ventilation for firefighting and life safety. For example, this example is a staircase pressurization. Just to take note, next week, same timing, we will have another training for staircase pressurization control, given to us by Engineer Randy Eugenio. Okay. So this is one purpose of ventilation, to have firefighting and life safety systems. Another one is also under life safety and firefighting is smoke exhaust fan. Smoke exhaust fan. We had a training for this one last week. So if you are interested of learning and going through the recorded training from last week, drop me an email and we can send you a copy. So ventilation is used to extract smoke extract or de-smoke. They call this system a de-smoke system. Another one is the kitchen for controlling impurities. So we also use ventilation to suck up the smoke and impurities created by the food that we cook. Again, we have discussed this one. This is for car parts so that we can maintain the CO2 or carbon dioxide and carbon monoxide concentration within the space. And this one is for chemical. This one is a laboratory fume hood. So we also use ventilation principles and ventilation requirements so that the fumes from the chemicals will not impact or will not seep out to the laboratory technicians and scientists, so that it will be safe for them to handle chemicals. This is chemical cabinets, chemical storage. So we also use ventilation. So you can see these ventilation ducts connected to the cabinets so that those hazardous fumes created by the chemicals stored inside will not be leaked. So in conclusion, before we conclude, any question? Question? No question. All right. So in conclusion, the ventilation is required based on three principles. First is to ventilate space, ventilate according to requirements, and ventilate according to pressurization. Always use local codes. Our local code here in Singapore is SS553 before you even try to touch the international code. International code is ASHRAE 62.1. Thank you very much. Any questions that I can take? Question, is the computation of ventilation is the same for aircon computation? I will get back to you. Let's get back to the slide. I think I shown one slide. Oh, here. Okay. There you go. All right. So earlier we have shown this what do you call this example. This one is nearby air conditioning load. Okay, one aspect that says this is for ventilation only is this one, specific heat ratio. Specific heat ratio for air conditioning on this space. Then yes, if your specific heat ratio is 100%, then yes, the ventilation is the same as aircon computation. But if your SHR is not 100%, then you would have a different calculation. You have extra few steps to carry out. But if you're only considering sensible heat, then yes, we are using the same formula. So we are using the same principle for the air conditioning and ventilation. Thank you, Joseph. That's a good question. Any more question? Any more? We are welcome. You guys are welcome to post any question, to say any question you would like. Wala na? If not, if there's no more question, then I would extend my warmest gratitude for spending your evening with me. Don't forget, next week we will be having staircase pressurization given to us by Engineer Randy Eugenio. If you have any questions popping up into your head next time, you can drop me at my email at evenlearning.su@gmail.com, or you can drop me on my mobile at 9389518. Okay? So if there's no more, I won't keep you up. Thank you very much, guys. Good evening and see you again next week.